So thinking back to your days of math before this class, when you looked at functions, the idea of symmetry came into it. And we talked a little about symmetry on the circle, but I want to talk about symmetry of the graphs of these trig functions. So here, the sine has some symmetry to it, right? I have this upward part here, and I have a similar downward part there. This symmetry I have here is related to, it's called odd symmetry of a function. And think back to maybe y equals x raised to the third power from a previous class. This function also has odd symmetry. It's a rotational symmetry. I can rotate this graph 180 degrees and get the same exact shape. And the real definition of odd symmetry is not just the graph, but it's a little bit of algebra. I just want to point that algebra out. So function symmetry. There's an idea you saw in a previous math class called odd symmetry. It's also symmetry through the origin. It's a rotational symmetry of 180 degrees. And then algebraically, a function has odd symmetry if you replace x with a negative x, and that negative pops out, positive x inside, then for all values of x, this is the definition for odd symmetry. So this is the algebraic definition. So I pointed out the cubic function before, y equals x cubed. And think about just plugging in x equals 2. F of 2 is 2 cubed, which is 8. If we plug in x equals -2, f of -2 is -2 cubed, which is -8. So kind of looking at the definition here, if I plug in a negative, I could also look at it as the negative popping out. So if I just use that idea, this definition with the 2 I was using, this says f of -2 should equal the opposite of f of 2. We just calculated that f of 2 is -8. Sorry, f of -2 is -8. We know that f of 2 is 8, and then we're putting a negative on the outside. Right, so that's just a numerical example of it. Other way to check is actually to do algebra on that statement. So take the f of -x. Normally, I would just write x cubed, but I'm replacing x with a -x. To cube something means to multiply by itself a couple times. Negative times a negative is a positive, times another negative is a negative. X times x times x is x cubed. The negative popped out. So that is negative f of x. So that's like an algebraic proof. That this function is definitely odd symmetric. Okay, and I could see it in the graph. Now it turns out the sine is also odd symmetric. The sine of -x is always the same as the sine of x. And we can see that, sorry, the opposite of the sine of x. And we can see that in the unit circle, we can see that in the graph of the sine. So sine is an odd symmetric function. Even symmetry is another idea from a previous math class. Hopefully you remember. If not, I'll refresh your memory. Even symmetry is symmetry about the x-axis. I lied. Y-axis. Symmetry about the x-axis at any function. And the definition there is it doesn't matter whether you plug in a negative x or a positive x, you're going to get the same result. classic example of even symmetry is y equals x squared, because it doesn't matter whether you score a positive or a negative number, you're going to get the same thing, right? So if I plug in a negative x there, that's negative x times negative x. Negative times a negative is a positive. X times x is x squared. The negative disappears. It doesn't matter. That's the idea of even symmetry. The cosine has even symmetry. So the cosine of a negative x value is exactly the same as the cosine of that x value. So one way to think about it is algebraically, negatives don't matter if you're even symmetric. If you're odd symmetric, negatives pop out. Okay, two different ways to think about that. Other trig functions that follow these patterns, turns out because tangent is sine over cosine, the tangent is odd symmetric. Tangent of negative x is equal to the tangent of x. Same thing with the cotangent, because the sine is involved. And then the secant, let's see, no, cosecant is related to the sine, it's 1 over, so the cosecant is also odd symmetric. Oops, and I'm forgetting something. Negative, negative, parentheses, negative, cosecant of x. So those are all odd symmetric. Even symmetric, we've got the cosine, and we've got the 1 over cosine of secant. Because of that reciprocal relationship between cosine and secant. And so those first couple of homework questions are related to that idea. Oops, let me get the homework. Come on, Zoom, behave. So this says the tangent of x equals -5. Can we tell what the tangent of negative x is? So let me just grab a screenshot of that. So just reminders of some things I went over a moment ago, is that the sine and the tangent are odd symmetric. So for example, the sine of negative x equals the negative sine of x. That's the definition of odd symmetry. Similarly, the tangent of negative x is the opposite of the tangent of x. So we switch the sign inside, the sign switches outside. Conversely, we have the idea of even symmetric, like the cosine, negatives disappear. So with this first one right here, they say the cosine of x, and they really should have parentheses there, is -1.5. What would the tangent of negative x be? Well, the negative would change the sign on the outside, so it should be 1.5 because of its odd symmetry nature. The sine of x is 0.6, so the sign of negative x should flip the signs. That should be -0.6. Cosine is even, doesn't matter if you plug in a negative or not, it's still going to be 0.2. And then the pi plus x, we have to think about then a shift of the tangent. What does that do? Well, remember for this one, what's the period of the tangent? It is pi. Definition of a period function is if you shift over pi, the same stuff's going to happen. So if the tangent of x is 1, then the tangent of pi plus x has to be 1 over, because that's the period of this function.